My name's Andy. I'm the chief scientist at Continuum Analytics. My background, as Travis talked about, was high-performance computing, doing computational mathematics, and I also help run the NumFocus Foundation. And so I have experience in a whole bunch of different vectors and whatnot, but moving on because I'm boring. So Continuum Analytics, just to give you a little bit of understanding of who we are and what we do, is so we build technologies that enable analysts and data scientists to answer questions. And the questions are all around us. And we come from the open source community, which means that we're highly dedicated to open source code. And if you peruse through the schedule today, you will see a whole host of our open source code being demonstrated throughout the day. So what does that mean for most people? At some company, you have a terabyte of data laying around, and we're the guys help you explore it. And we do it through a full stack of different tools, from Anaconda, which gives you about 200 different packages to easily install. Conda, which will allow you to manage your environments and do package managing. Numba, a compiler to speed up Python. Blaze, which I'll talk a little bit about, to scale to massive amounts of data, and we have a couple of the Blaze core devs here in the room. And Bokeh, which will help you get those pretty plots of cats into your browser, because that's what we all want to do, really. And then at the end of the day, we have to share and deploy our code with Wakari. So that's kind of the Continuum suite of stacks. But today, my goal is to talk about this in Hadoop. So great, you have a jerk with a lot of titles and a stack of software to sell you. So what do I do what kind of problems do I solve? So I came from computational scientists, so we took equations like these and solved, okay, this video, is that video going to play? Nope, all right. So what I used to say, problems, math equations to this, and this is supposed to be a little GIF that shows a wave going back and forth, to solve on your desktop, and take them to the massive scaling machines like this in the corner, and my slides are all messed up here, very sorry. To the machines like this, which is 6,000 nodes of very very dense memory and compute machines running up to, I think, 25,000 processes. To solve problems that look like that, where you have a storm surge coming in and you want to know if your city is going to be underwater. So that's the problems I used to solve. Thank you very much. And so the question is, why is this interesting to Hadoop? Well, it turns out now the problems I solve start with HTML files and free text, go to machines that look like this, which is literally, if you Google image Hadoop cluster, that is what you get. I'm not trying to be pejorative. I'm just representing Google here, using the wonderful scikit-learn tools and the other pieces of the Python ecosystem to get out data, an understanding of that data coming in, to solve problems like human trafficking and find out where Ebola is spreading and things like that. So going from big math to big data is kind of my transition in life, and why I'm here talking to you about Python and Hadoop. All right, so what am I actually really here to talk about? First, I want to go through a little bit of a discussion about where the Hadoop system is, where Python is in that Hadoop system. And then we had a time cut a little bit short just because we had all the people coming up downstairs. So we're going to try and end on time. So I'll probably briefly go through Blaze and Bokeh and how you interact with the Hadoop system with those open source tools. So first, let's talk about the ecosystem. So large-scale data analytics. Our view of the world comes in 4 different areas. We have BI tools, distributed systems, scientific computing, like I showed you at the very beginning, and then stats and machine learning and domain modeling. So first off, a lot of people in the finance world love their BI tools. They stare at them all day, and you can see screens of numbers at high density. So we have to work with things like MySQL or Mongo and interact with the standard BI tools, because that's how you get onto those GUIs that you have 8 screens and financial folks can destroy our market, which is a good thing. Second, we have tons of tools to do machine learning, and here we have we'll have scikit-learn talks and pandas talks later on today. And so how do we actually get these things to work? And a lot of these guys are built on top of scientific computing tools, which is where I came from with, for example, NumPy, which Travis built so long ago. And new things like B calls, which gives us a very fast interface to the disk storage, compressed disk storage. And now the new kind of kids in town of distributed systems using Hadoop, Spark, Hive, and things like Hive and Impala. The interaction with these traditionally goes something like this, where the distributed systems talk to your BI tools and you have nice queries, and maybe you pull out that data from that nice query and pipe it over to pandas or scikit-learn. And from that, you might talk to a scientific computing stack, but very rarely did you actually have the scientific computing stack actually talk to the distributed system inside the Hadoop world. Now, in the MPI world and the supercomputing world, you did that backwards. You always went to the distributed system first. And now we have a few places that are trying to cross over, like Mahoop and R Hadoop and things like that, but from the machine learning side to the Spark systems and whatnot. So what kind of animations. So that architecture there has been often turned into something like the Lambda architecture. And I usually show this slide so people kind of know what we're talking about, where you have batch layers, serving layers, and speed layers. So I stream data in, and I usually go to that top layer where all the interesting things happen, at least for me. And I do a lot of Hadoop processing and a lot of data processing, and that comes back into a serving layer, into a database, or however you might prefer your data. Of course, there's always a lot of people in the room. I'll speak a little bit about Parsley's tools that want to go straight to that stream layer and just speed through and see incremental updates throughout. So that bottom layer kind of takes us to that speed layer. And there's a lot of different systems out there that are providing this kind of random architecture. For example, you have the base Hadoop stack, which you kind of have a whole zoo there with HDFS, Hive, HBase, and whatnot. And then there's the Berkeley Data Science stack, which, if you don't know, I think it's pronounced Badass stack. At least that's what they call it. And so I always enjoyed that. But here they've taken a lot of the Hadoop layer and replaced it with things that we know are much faster, like adding Spark and Tachyon, which gives you a distributed caching layer, and then having a single stack that, on top of that, uses Scala, which could be a much nicer way to program, but also do streaming, and there's this is a little old, this slide, but you have like SQL APIs and things like that. And so there's lots of stacks, lots of different ways people are interacting that. But where exactly is Python in this world? And so Python ends up being in several different places. The first one is kind of Python as a driver. So we see, so today if you go ask around 20 different people, you get 30 different answers, but they'll all say at least these three, right? PySpark, which is a really great layer. How many people have used PySpark in the room? How many people have used Spark in the room? How many people use Hadoop in the room? How many people use a computer in the room? All right, that guy's asleep. All right, there you go. Raise your hand. All right, there we go. Okay. So if you use a computer, go use PySpark. It's amazing. It will get you. They used to talk about how wonderful you could get distributed computing up, and PySpark is the closest thing I've ever seen to go from a single script to a really distributed computing script. MapReduce kind of promised us that, and then everyone realized, oh wait, this is hard to use. PySpark is actually a lot nicer to use. You load up your text file, it just kind of works very nicely. The second thing that people talk about is Hadoop streaming. How many people have used cat? Okay, how many people know what cat? Well, how many people know what cat is? How many people use Unix? Okay. All right, so cat is a Unix tool that just streams out a file, right? So Hadoop streaming is just stream out a file into another program. We've all used Python, so that's good, into a text file, and we've all used text files. That's all you have to know to use Hadoop streaming. Cat a file into a file and put it into another file. And so Hadoop streaming is another really nice way to take a single, very small script to do that sort of thing. But it is at a very granular level, right? A single script that I can put in and emulate on my desktop as if it were cat Python program file. And it's a very nice kind of Unixy system. But at the same time, once again, it's not really designed to solve these large distributed problems, or these large highly coupled parallel problems. And then there's Pig, which is, because Hadoop's hard, it went and developed a data flow language called Pig, which you can then put in a really nice Python scripts inside of those. Although once again, same limitations of Hadoop streaming. The next kind of area where a lot of people are using Hadoop and Python is the Python as the UDF driver. And so UDF just stands for user-defined function. Typically, you think of, like, for example, a Postgres a SQL hook or like a trigger that would you store a function into the database, and then whenever something happens, it fires off that database for certain calls and whatnot. It's always been a very nice concept, but you would always say, well, why do I need to store Python into the database when I can just call pandas and actually manipulate it as if it were a script? So it's always been something that's not super compelling for me until you get to a system where your database is actually distributed through the entire 4 nodes that we saw, or 20,000 nodes if you're Twitter. And so there's two of the bigger codes I know of, and there's obviously a lot more. But two that we kind of worked one we worked with Cloudera's Impala, which is a database engine built on top of HDFS. And they actually took our number-based tool that speeds up Python and produces a LLVM code block for them. And so any Python code can be compiled from Numba and run inside the database. So then it will be a very easy way to fire up throw in all your SQL data and then fire up a Python script inside the database that actually runs distributed over the entire cluster. The other way to do this is Hive, is a little more traditional. I'm told that it leaves a lot of speed on the table, so I usually point people to Impala. But if you have the latest Hortonworks distribution and you realize that, oh, that's Cloudera and we have to use Hortonworks, Hive is your answer. So, and Hive does a very similar thing, although they run a native Python that serializes instead of using kind of a code injection like Impala does. All right, but what about that speed layer we just talked about? And so I want to take a few moments to talk a little bit about who you go talk to about that bottom layer. And there's basically two different codes that I use. Parsley's Stream Parse, which uses Apache Storm. So how many people know what Apache Storm is? Okay, a good number. So Apache Storm is a parsing, or is a stream manager that takes, I guess they call them sprouts and bolts. And so you write little bolt programs that then produce spouts, and those go into your new bolt program. So think of it as a fractal Hadoop streaming, if you will. And so Parsley has a really nice code for setting this up, and I definitely recommend going and checking out their stream parts, and they have a whole topology and things like that. So any data coming in, you throw it into your Storm topology. It then goes to your MapReduce, or your cluster workers, and then goes out to your different files and whatnot. And Parsley's tool is the amazing one to use. Then there's Kafka, which, how many people know what Kafka is? Okay, so I really should have spent a lot more time going through all these tools. So Kafka is a log commit, is a log manager that basically takes another stream and commits it to a global log, and then creates streams off of that global log. And so Kafka Python has a really nice protocol if you have huge amounts of data. I guess the big point of the story there is that Kafka can manage if you have data that you can't actually really process because you just have so much. So for example, I have lots of spurts of data coming at me. Kafka is the thing you want to use because it can handle that spurts of data, and then once that spurt of data kind of dies out, then your speed layer, your batch layer can take care of it a lot more. And so by just focusing on a single log, and then bringing pipes out of that log, you get the same sort of speed. The cool thing about these guys is they're both reproducible. So if I have a stream and I want to run this code again, I produce another stream, it'll run the same code, which is a really cool feat. If you ever want to read a really neat paper about how that's done, the Apache Storm paper on storing triples and getting reproducibility out of these large streaming systems is very cool. Okay. So that's kind of my view of some of the codes you should know about in the Python ecosystem. I wanted to kind of go into kind of how we use these things at Austin in Continuum. So it's great. All I see is pictures. What does this really do for me? So me, being someone who doesn't want to do any work, I tell, hey, Genie, give me a Hadoop. And then that didn't really work. So we built this code called Anaconda Cluster. So Anaconda Cluster is a new product at Continuum that basically takes the Anaconda stack and will load it up on your cluster for you. So all the things you do in Anaconda, where you create your environment and your Python ecosystem, saying you want which packages you want, it basically will help you deploy on that cluster. And it works something like this. I say, Conda, please create me a demo cluster. And for the example here, I say, give me a simple AWS with 3 nodes. And I can even tell you which size of machine I want for AWS, and it works for DigitalOcean and some other things. And I can give, for example, a image, in this case, a simple image like that. And that guy goes and spins us up a Spark cluster, which also runs CDH, so you can run Hive and HBase and other things on it as well. So, great. What do I do with that? I asked the Genie to give me a useful cluster. And what is a useful cluster? For the purpose of this demo, we're going to find that as Anaconda plus Numba. So everybody knows what Anaconda is, right? Okay, there we go. Everybody's shaking their head. Awesome. That's what I like to hear. And I talked a little bit about Numba. Maybe I should talk a little bit more. So Numba basically takes Python code, you add a JIT flag to it, and it turns it into LLVM code, which is pretty nice because LLVM works pretty much everywhere these days. Thank you, Apple. And we can hit, if you buy the Pro version, right, you get to work on GPUs and fancy architectures and whatnot. But if nothing else, you can use the standard version, and I believe Jake Vanderplas's examples of getting 1500x speed up and things like that. I don't think that was this code, but it was something like it, right? And so here, for example, you can do a real kind of interesting updates to very large matrices and things like that, although we're just doing 3x3s here. So that's what Numba does. It takes Python and NumPy code, produces LLVM code. So the first thing I say is Conda cluster, please manage my cluster. And so we have this, we haven't completely figured out the CLI to this thing, but it'll get better. So I tell it, give me a demo cluster and please create me a test environment. And on that I say, give me Python, give me NumPy, give me Numba, and so on and so forth. And then I say, Genie, make Spark faster. And so I'll put these slides up later so you can study this gist in much detail. And so we have a gist of using Spark and Numba inside a Spark routine. And let me go through kind of the interesting parts right now. So first you create a Spark context. So all this guy does is go and sets up an app and sets up your machine and tells the machine, like, I'm taking over, and whenever you do whatnot. I have so MUF and iters and partitions are numbers that come down from a function. So I create some matrices on this function. And I have some random matrix I create. And then I broadcast those matrices throughout my cluster. So this broadcast just puts it throughout the cluster there. And so then I say I have to parallelize this function here. And so I say parallelize this map into these partitions, map this update function with a whole bunch of values, and we'll talk about this update. And at the end of that, I will have a matrix MS that I can then broadcast throughout and then parallelize another matrix computation. What this guy is doing ALS, which is an alternative alternating least squares. That's what it was. And so so alternating least squares basically it's going to have a couple of matrix multipliers and reduction, or matrix vectors, which is usually the level I think of anyways. And so this is what the update guy looks like. So I have my matrix transpose matrix on the right side here, and you notice here matrix multiply. Well, that's done pretty well by NumPy, especially if you have the MKL bindings and everything set up in your cluster, which the cluster kind of comes with typically, or at least when I set it up. Then you have your nonlinear updates, and this was where we actually add the JIT code. So all we're actually JITting is this code right here, because everything else in this code is basically math, right? So we can use low-level BLAS libraries and things like that. But there's that one update function. If you try to parallelize that guy, it ends up being, I think, on the order of 60% of our time. And so we were able to speed up this one function by, I think, several orders, or well, I think one order of magnitude, so several times, but speeding up the whole thing like I think 2 times or something like that. And so in here, we just JIT add, and we actually add into this function a lambda, which is a parameter that comes through the function, and that UU, which came from our XTX, the transpose guy there. So this is an example of how to use these things. So you can very easily go in, manipulate in a simple Python manner, but then you can JIT any code that is kind of the slow part of Python typically, and all of a sudden you have a very natural way of working with this code. And this code isn't so bad. You have to do a few bits of magic to broadcast things out, but then you can just go into your update function and you're off to the races with PySpark and using Spark and the entire ecosystem. All right, so then the other kind of challenging part to this is how do I actually run this guy, because there's at least 10 different ways to run in Hadoop, whether you're using Yarn or Mesos or whatnot. And so our cluster will launch the script with a very kind of launch the script on this cluster with whatever we name the script and whatnot. Just so you guys know this is actually works. We made a demo video, and since I'm not mirroring my screen, let me. And so the script works something like this. So we create the cluster. Is it playing? It's not playing. All right. It's like I created a video, so I wouldn't have like a problem with it. So more or less, you create a cluster, and it goes off and does the. It uses libcloud to interface with the cloud computing environment, so it does work on any environment that we can get libcloud to work on, including in-house environments and whatnot. And so this actually takes a little bit of time to work. So we have another window that will open up here. Never mind that. And so, all right, so finally we get Salt coming up, and we start setting up the machine and so on, and it'll go through and set up very large machines or very small machines, as this case goes, and we're testing a lot on AWS. Just so this code is still in beta. We're still testing out a lot. We hope to release something for open source folks to use within the couple of days. And so it's just a conda command. You upload with conda, and for example, I register some clusters with it, and you can do conda commands that list the different clusters we have. For example, there's a PyData demo I think Matt might be using later today, although I don't think he's using this tool. And so we're still setting up that machine. Now we can. And you look at this guy, and basically all we're doing is saying, give me some IP addresses, and you can even tell me what the providers are and what you actually want on the machine inside this YAML file that just sits alongside your conda RC file. The next thing we kind of do is show how to set environments here. Let me make this bigger here. So there's a help command. We have, for example, list info, set environments, create. Kind of in the bootstrap is kind of like I just want to bootstrap a mini conda cluster. So now here the demo and take some info on what is actually running on that guy and see when it's up. And all right, there we go. We have a root install of Anaconda and opt Anaconda. So now we're ready to go. But I do need to create my test environment. And so as a quick example, that Python 2.7 and NumPy. And so what this guy's going to do is it's going to set up an environment and then create that what packages need to be installed, and then you'll have to say push environment, and it will then push it out to your cluster. So instead of so we're going to add for example a stream example as well. And so this will push it out to the cluster a little bit faster, and you can see how it's streaming it out to the cluster and putting in the opt Anaconda bin to 4 different places. And there's your standard cluster standard environment for Conda. Now it's Conda on a cluster. And when we call info, we see now we have 3 different environments: the root environment, dev environment, and dev1 environment that we can play with. And so we set an environment here, and now we're ready to go to start launching clusters. And this command should work. Of course, if anyone who's ever used a cluster, you realize it doesn't necessarily respond as fast as you want every day, and so we have some work to fix some of that. So that's more or less the idea of how we kind of set up clusters, manage clusters, and move to the Hadoop ecosystem. So let me start the. So that's Anaconda cluster. If you're interested in trying out a beta copy, definitely there's a contact us button on the website, and or come talk to me. So that's if you actually want to Hadoop. How many people are going to go use Hadoop now? Oh man, that's a fail whale right there. All right. So how do sane people use this? Well, we have 2 codes that Blaze and Bouquet, which I'll briefly go over. I don't want to steal the thunder. Matt Rockland's giving a talk later about Blaze, and there's Brian Vandeven, who I don't see in the room, who will be talking about Bouquet in much more detail. I'm just going to give a very high-level overview. So, so in this ecosystem, you saw a lot of tools, a lot of different ways of interacting with the data, but this basically, most people's viewpoint is it's just really a pain to use. And we're definitely trying to build tools to make it much easier to use for the Python ecosystem. But with this pain, we have another tool called Blaze. And the basic idea of Blaze is to build a tool that actually helps you with your needs. So as any tool, you have something that fits the problem, you have something that fits the person. And if you actually want to interact with this entire, I don't know if I'm stealing your thunder, Matt. I did steal your, okay, good. These were his slides, I think. Okay, no, all right. They came from the drive. But the problem with this, right, is this is the typical idea of like every problem becomes a hammer, so we end up being, or a nail, and we end up with thousands of tools. So in any carpenter's bag, you will have a whole lot of tools. Now, just like nobody was interested in Hadoop in this crowd, nobody's really interested in buying all these tools just to fix their kitchen, right, or fix their faucet. And so we have a whole ride of things. So this fits the problem. Now we want something that actually fits the user. And so lots of people probably bought a tool like this. I'm guessing many more people have bought this tool than have bought all those tools on the previous page. And this is just the Dremel tool. Right? So Blaze provides an easy interface to interact with all these tools in a way that is nice and pluggable and actually works throughout the Python ecosystem, because we love Python. And so to bring it back to that very first kind of diagram of the world of large database, large distributed applications, we have Blaze in the middle that actually talks to these distributed systems that can push that code. So I set up a Spark cluster. Nobody was going to use it, but if you use Blaze, you might actually use it anyways, because we actually do have a lot of Spark and Impala codes inside Blaze that can take the same pandas code you ran and run it on Blaze. So it becomes a very easy way to interact with scientific computing, machine learning, BI tools, and whatnot to get that same sort of system so you don't have to learn all these tools at once. Of course, everybody looks at this and they say, well, that's a little bit magical. How in the world does that work? Well, we use a very easy trick called lazy evaluation and symbolic manipulation. So we have the Blaze kind of triangle, as my colleague Christine Doig, who made this slide, likes to call it. We have abstract expressions at the top, so things like your split, apply, combine, your filters, your projections, and so on and so forth. Then we join those guys up with data sources handling, literally hundreds of data sources that Python can throw at us, from CSV to HDF5 to JSON and data frames and so on and so forth, to those computational backends. So you might not be very interested in using Spark and using distributed computing, but if you had a problem that requires that, it's nice to have a tool that can then easily transfer to using those big machines as opposed to only your desktop. And that's where Blaze can come in and transfer your Pandas code to a Spark code. And I'll show an example of doing that in just a minute. So that's the idea of Blaze. To give an architectural diagram, I realize Matt's probably thrown this away after I made it. But I view our architectures, we have an API so that everybody can hit and use, and it's the same API throughout. We build deferred expressions and have an interpreter layer that then talks to our data layers and our compute layers. We try to keep the user away from the compute layer as much as possible, although often what happens is you set up something with pandas and whatnot and then pass it off to Blaze, and then we drive it from there. We can't keep you away from the data layer because that's everywhere, and we can't possibly get to know everything about your data. So that's kind of the kind of baseline architecture of what we do. To give an example, we had to join the web with the web, which this is an example of using the Common Crawls hyperlink graph. So here we have an expression, and the table symbol is deprecated, so don't use this code anymore. Go listen to Matt Rockland. And so where we take these ARC files that gives us the name, the URL that you will find your websites at, and the node into the graph that would then tells us the connectivity of the graph. We have the ARC files that tell us the connectivity of the graph, that node ID, and its out neighbors and in neighbors. And we join this guy based upon that node ID, so it's a very simple example. I hope that you all don't get to work with only four-row graphs, because that we can actually, or four-row tables, because we can actually do that very well. So anyone with thousands of rows? No, yeah, there we go. This one guy. All right. So in finance world, you always find these nice tables that are like, that should be inverted, right? That's not okay. So this by operator comes from the split apply combine notion, so it looks a lot like R. We join on the name of that node, and we just count the rows. So all this guy is doing is going out, counting how big your footprint is on the web. And for example, I load data, which I'll show you in just a minute, which is the part where you can switch from different places. In the computation, it says compute. It figures out what your data and your compute system is based upon that data. And then you can have a dictionary-like access to things like how big is Blogspot's footprint. Here's the load data. Basically, using Spark and HDFS, looks a lot like the code I showed you before. I just say, give me a Spark context, give me a text file, which is a distributed text file, map over that text file, how to actually split this thing out so that I can read it as two numbers. And I do the same thing with the ARC file. Or I use pandas if I'm going on local disk, so I just open a file like you open a file in Python as normal. And I do the same thing where I split the file, say how do I read the two numbers out of every line of that file. And so there I have my ARC and index files, which then computed. And this guy worked on my laptop and a cluster of, I think the cluster is around 600 nodes. So straight off, want to learn more, go talk to Matt Rockland. We have webinars and blog posts and whatnot. And I have 2 minutes, so I will just show Bouquet and take questions. The second part of this is, all right, so you can use tables, you can do manipulations that can hit a very large Hadoop cluster. What about when I want to show those cat videos? Well, we have a data visualization library called Bouquet that does novel graphics, and it's bouquet at PyData.org. And it does interactive visualizations in your browser and can stream large dynamic data and do an algorithm we call abstract rendering to do incredibly smart downsampling. So if you have a lot of overplotting, so if you just plot big data, you usually just get, for example, a map that's just the population of the world. We often have a lot of abstract rendering, so you can put in and say, hey, I don't want the population of the world, I want the difference in population, the per capita, or something like that. So it gives you a much smarter way of adding abstract downsampling. And the big thing here is no need to write JavaScript, and we use Matplotlib capability. And so we don't like writing JavaScript, so we wrote a whole lot of it so you don't have to. And there's a whole lot of kind of nice visualizations. I think Karan is also going to show using some really nice widgets as well, and building dashboards and very functional kind of things. Go see Brian to see what's cool and what's up to date. Go see Karan to actually see a grunt in the field using this thing. All right, so here's some more kind of visualizations of it. Thank you very much for your time, and I think I have time for at least one question.